The universe, in all its grandeur, is composed of fundamental building blocks. We call these elements. Imagine, if you will, a grand canvas upon which these elements are meticulously arranged. This, my friends, is the periodic table. It's not merely a chart. It's a symphony of science, a testament to human ingenuity. Each element, a note in this grand orchestra, plays a unique and vital role in the composition of our world. From the air we breathe to the ground we walk upon, the elements are the very essence of our existence. But this intricate tapestry of elements is not random. Oh no, far from it. There's a beautiful order, a hidden logic that governs their arrangement. Join me, dear viewers, as we embark on an enthralling journey to unlock the secrets of the periodic table, right here on Sperlin TV. Don't forget to subscribe and hit that notification bell to join us on this illuminating adventure. Our story begins in the mid-19th century with a brilliant Russian chemist, Dmitry Mendeleev. Picture him, if you will, toiling away in his lab, surrounded by stacks of books and vials of colourful solutions. Mendeleev was obsessed with understanding the elements, their properties, and the relationships between them. He had this ingenious idea of arranging the elements in order of increasing atomic weight, like organising books on a shelf by their sides. As he did so, a remarkable pattern emerged. Elements with similar properties seemed to recur at regular intervals, like the repeating chorus of a captivating melody. This profound realization led to the formulation of the periodic law, a cornerstone of modern chemistry. Mendeleev's periodic table was not just a static arrangement, it was a predictive tool, a roadmap for future discoveries. It even had gaps, you see, spaces reserved for elements yet unknown, elements that would later be discovered, confirming the brilliance of his insight. Now, let's delve deeper into the heart of the periodic table. Each element, represented by a unique symbol, is defined by its atomic number, the number of protons in its nucleus. Think of protons as tiny, positively charged particles that reside at the atom's core. The periodic table is arranged into rows called periods and columns called groups. Elements in the same group share similar chemical properties, like members of a family with shared traits. As we move across a period, the properties of the elements change gradually and predictably, like the subtle variations in the colours of a rainbow. Over the next few segments, we'll embark on a captivating exploration of the first 92 elements, from the simplest, hydrogen, to the more complex uranium. We'll uncover their unique characteristics, their roles in our world, and the fascinating stories they tell. So, fasten your intellectual seatbelts and prepare to be amazed by the wonders of the periodic table, only on Sperlin TV. Don't forget to subscribe and let the exploration begin. Our journey through the periodic table begins with the simplest and most abundant elements in the universe, hydrogen and helium. Picture, if you will, the fiery birth of the cosmos, the Big Bang. In that primordial inferno, hydrogen, a lone proton with a single electron, emerged as the firstborn element. As the universe cooled and expanded, hydrogen atoms, drawn together by gravity, ignited in the hearts of stars, fusing to form helium, the second element on our periodic table. Helium, with its 2 protons and 2 neutrons, is a noble gas, aloof and unreactive, content in its own stability. Hydrogen, the cosmic fuel, continues to power the stars, including our very own sun. It's the lightest element, highly flammable and essential for life as we know it. Helium, on the other hand, with its low density and inert nature, finds its niche in balloons, blimps, and cooling superconducting magnets. From the vast expanse of space to our everyday lives, hydrogen and helium, the cosmic pioneers, remind us of the interconnectedness of the universe and the elegant simplicity of the periodic table. Think of hydrogen as the energetic child, always eager to react and combine, while helium is the calm and collected elder, content in its own company. Hydrogen, with its single electron, is always seeking a partner to share, while helium, with its electron shell complete, is perfectly content on its own. This fundamental difference in their electron configurations dictates their vastly different personalities in the chemical world. Hydrogen, highly reactive, forms bonds with almost every other element, while helium, the introvert, prefers to remain solitary. And yet, despite their contrasting personalities, hydrogen and helium share a profound cosmic connection. They are the products of the Big Bang, the fundamental building blocks from which all other elements are formed. Their story is a testament to the power of the periodic table, a tool that allows us to understand not only the properties of individual elements, but also their interconnectedness and their cosmic origins. Section 2. Lithium to neon, building blocks of life and light. As we move beyond hydrogen and helium, we encounter the second period of the periodic table, where we meet elements crucial for life and light: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Each element in this period, with its unique atomic structure, contributes to the richness and diversity of our world. Lithium, the lightest metal, known for its mood-stabilizing properties, powers batteries that fuel our modern lives. Beryllium, a strong but lightweight metal, finds its niche in aerospace engineering and X-ray equipment. Boron, a metalloid, exhibits properties of both metals and non-metals, making it useful in semiconductors and heat-resistant materials. Carbon, the backbone of life as we know it, forms the scaffolding for an astonishing array of organic molecules, from DNA to diamonds. Nitrogen, an essential component of proteins and nucleic acids, sustains life and fuels plant growth. Oxygen, the breath of life, supports combustion and enables us to breathe. Fluorine, the most reactive element, strengthens tooth enamel and plays a role in refrigerants. And finally, neon, another noble gas with its characteristic red-orange glow when electrically charged, illuminates our signs and lights. From the lithium batteries that power our phones to the oxygen we breathe, these elements are woven into the very fabric of our existence. They are the building blocks of life, the ingredients of light, and the foundation of countless technologies. Consider the intricate dance of carbon, nitrogen, and oxygen in the formation of DNA, the blueprint of life. Carbon, with its 4 bonding sites, forms the backbone of the DNA molecule, providing a stable framework for the other elements to attach. Nitrogen, with its ability to form 3 bonds, connects with carbon and hydrogen, creating the nitrogenous bases that encode genetic information. Oxygen, with its 2 bonding sites, bridges the gaps, holding the DNA strands together in a double helix. This intricate interplay of elements, dictated by their atomic structure and bonding capabilities, highlights the elegance and complexity of the natural world. The periodic table, like a cosmic recipe book, reveals the ingredients and the rules that govern the formation of everything we see and touch. Section 3. Unveiling the Octet Rule, a Chemical Symphony. As we journey through the periodic table, a fundamental principle emerges: the Octet Rule. This rule, like a conductor's baton, orchestrates the interactions between atoms, dictating how they bond to form molecules. The Octet Rule states that atoms tend to gain, lose, or share electrons in order to achieve a stable configuration of 8 electrons in their outermost shell, just like the noble gases. Think of it as a chemical desire for stability, a quest for a full outer shell of electrons. Elements in the same group, like members of a well-coordinated orchestra, share similar chemical properties because they have the same number of valence electrons, those residing in the outermost shell. These valence electrons, like skilled musicians, are responsible for forming bonds and creating chemical compounds. For instance, sodium with 1 valence electron readily donates it to chlorine, which has 7. This exchange of electrons, like a harmonious duet, results in the formation of sodium chloride, common table salt. The Octet Rule, a fundamental principle in chemistry, helps us understand the behavior of elements and predict the types of compounds they will form. It's a testament to the predictive power of the periodic table, a tool that allows us to unravel the mysteries of the chemical world. Imagine sodium, an alkali metal, eager to shed its lone valence electron like a performer yearning to take the stage. Chlorine, a halogen with its nearly full outer shell, eagerly awaits the arrival of an electron to complete its octet. Their encounter, a chemical reaction fueled by the Octet Rule, results in a transfer of the electron from sodium to chlorine. Sodium, now positively charged, and chlorine, negatively charged, attract each other, forming an ionic bond. This elegant exchange, driven by the quest for stability, results in the formation of sodium chloride, a compound with properties vastly different from its constituent elements. Sodium, a soft silvery metal, and chlorine, a poisonous gas, combine to form a stable, essential nutrient. The octet rule, a fundamental principle governing chemical bonding, highlights the transformative power of chemical reactions. It reminds us that the periodic table is not merely a collection of elements. It's a roadmap for understanding the intricate interactions that shape our world. And so, as we delve deeper into the periodic table, keep in mind this symphony of electrons, the octet rule, guiding the interactions between atoms and orchestrating the formation of the molecules that make up our universe. Section 1. Sodium to neon, from salt to fireworks. Welcome back to our illuminating journey through the periodic table, right here on Sperlin TV. We continue our exploration with the third period, where we encounter elements that are both familiar and extraordinary, from the sodium that flavors our food to the argon that glows within our lamps. Sodium, a highly reactive metal, forms the basis of table salt, a compound essential for life. Imagine, if you will, the salty tang of seawater, a testament to the abundance of sodium chloride in our oceans. Magnesium, a lightweight and strong metal, finds its niche in aircraft and car parts, where its strength and low density are highly valued. Aluminum, with its remarkable ability to resist corrosion, has become a mainstay in construction and packaging. Think of the sleek aluminum siding on buildings or the lightweight aluminum cans that hold our beverages. Silicon, a semiconductor, forms the heart of our digital world, powering the computers and smartphones we rely on every day. Phosphorus, essential for life, plays a crucial role in DNA, energy transfer and bone formation. Imagine the intricate double helix of DNA, with phosphorus atoms forming the backbone of this remarkable molecule. Sulfur, with its characteristic odor, is a key component of amino acids, the building blocks of proteins. Think of sodium, so reactive it bursts into flames upon contact with water, yet when combined with chlorine it forms a stable, essential compound. Magnesium, burning brightly, providing a brilliant white light in flares and fireworks, yet so strong and lightweight it enables airplanes to soar through the sky. Aluminum, extracted from bauxite ore through a complex process involving electrolysis, yet so versatile it can be molded into delicate foils or sturdy construction materials. Silicon, the foundation of our digital age, purified to extraordinary levels, enabling the creation of intricate microchips that power our modern world. These elements, each with its unique properties and applications, highlight the remarkable diversity of the periodic table and its profound impact on our lives. Section 2. Magnesium to argon, structural integrity and glowing signs. Continuing our journey through the third period, we encounter elements that provide structural integrity, illuminate our world, and even preserve our food. Chlorine, a highly reactive non-metal, disinfects our water and plays a role in the production of PVC, a versatile plastic. Imagine the clean, safe drinking water we enjoy, thanks in part to the disinfecting power of chlorine. Argon, a noble gas with its inert nature, finds its niche in lighting and welding, providing an inert atmosphere that prevents unwanted reactions. Think of the warm glow of an incandescent light bulb filled with argon to prolong the filament's life. Magnesium, as we've seen, contributes to lightweight structures, while aluminum provides strength and corrosion resistance. Silicon, the semiconductor extraordinaire, continues to revolutionize our world, enabling the miniaturization of electronics and the exponential growth of computing power. Phosphorus, essential for life, also plays a role in fertilizers, ensuring healthy plant growth and abundant food production. Sulfur, in addition to its role in amino acids, is used in the vulcanization of rubber, enhancing its durability and elasticity. Think of chlorine, so reactive it was used as a chemical weapon in World War I, yet so essential it disinfects our water and makes our lives safer. Argon, the silent guardian, protecting sensitive materials from oxidation during welding, its presence invisible yet crucial. These elements, from the structural to the essential, highlight the interconnectedness of the periodic table and its profound impact on our daily lives. Section 3. The Dance of Valence Electrons' Reactivity Trends. As we traverse the periodic table, we observe fascinating trends in reactivity, like observing the ebb and flow of a complex dance. Reactivity, the tendency of an element to undergo chemical reactions, depends on the arrangement of electrons, particularly those in the outermost shell, known as valence electrons. Elements in the same group, sharing the same number of valence electrons, exhibit similar reactivity patterns. Alkali metals like sodium and potassium with their single valence electron are highly reactive, eager to lose that electron to achieve a stable octet. Halogens like chlorine and bromine with 7 valence electrons are also highly reactive, but they're on a quest to gain an electron to complete their octet. Noble gases, on the other hand, with their full outer shells, are chemically inert, content in their stability. As we move across a period, reactivity tends to decrease. This is because the number of protons in the nucleus increases, pulling the electrons closer and making them less likely to be lost or shared. Understanding these reactivity trends helps us predict how elements will behave and interact with one another. It's a testament to the predictive power of the periodic table, a tool that allows us to unravel the mysteries of the chemical world. Think of alkaline metals like eager dancers, readily shedding their lone valence electron to join the noble gas configuration. Halogens like eager partners, readily accepting an electron to complete their outer shell and achieve stability. These trends in reactivity, governed by the arrangement of electrons, highlight the fundamental principles that underlie the periodic table. It's like a grand cosmic dance, with each element playing its part, its movements dictated by the invisible forces of atomic structure and the quest for stability. Join us next time on Sperling TV as we venture further into the periodic table, unraveling the mysteries of elements, their properties, and their profound impact on our world. Section 1. Transitioning to the D block, a sea of versatility. Welcome back to our grand exploration of the periodic table, right here on Sperling TV. Today we delve into the heart of the table, the D block, home to the transition metals. Picture, if you will, a shimmering sea of elements, each with its own unique luster and allure. Unlike the main group elements we've encountered thus far, transition metals exhibit a remarkable versatility in their properties and behavior. They are like chameleons of the periodic table, capable of changing their oxidation states, forming colorful compounds, and exhibiting magnetic properties. These remarkable abilities stem from the way their electrons are arranged. Unlike main group elements, which fill their outermost s and p orbitals, transition metals fill their d orbitals, located in the inner shells. These d electrons, like skilled artisans, can be readily shared or exchanged, giving rise to a dazzling array of chemical and physical properties. Think of iron, the quintessential transition metal. It can exist in multiple oxidation states, from Fe2+ to Fe3+, allowing it to participate in a wide range of chemical reactions. This versatility is what makes iron so essential for life, playing a crucial role in oxygen transport in our blood. Or consider copper, with its characteristic reddish-brown hue. Its ability to readily donate and accept electrons makes it an excellent conductor of electricity, hence its widespread use in electrical wiring. And let's not forget gold, the most noble of metals, prized for its resistance to corrosion and its lustrous beauty. The D block elements, a treasure trove of chemical diversity, are essential for countless technologies, from the catalysts that drive industrial processes to the pigments that color our world. Section 2. Scandium to zinc. From lightweight alloys to essential nutrients. As we navigate the D block, we encounter elements with a wide range of applications, from lightweight alloys to essential nutrients. Scandium, the first element in the D block, may not be a household name, but its alloys find use in high-intensity lighting and aerospace components. Titanium, known for its strength-to-weight ratio and corrosion resistance, has become a mainstay in aerospace, medical implants, and even jewelry. Imagine the sleek fuselage of a modern aircraft, crafted from titanium alloys that can withstand extreme temperatures and stresses. Vanadium, often added to steel to enhance its strength and toughness, plays a vital role in construction tools and even nuclear reactors. Chromium, with its shiny protective finish, is the key ingredient in stainless steel, preventing rust and corrosion in countless applications. Manganese, essential for plant growth, is also used in steelmaking to remove impurities and improve its hardness. Iron, as we've seen, is crucial for life and forms the backbone of countless structures, thanks to its abundance and versatility. Think of zinc, an essential nutrient found in oysters and other seafood, playing a crucial role in immune function and wound healing. It's also used in galvanizing steel, providing a protective coating that prevents rust. These elements, from the structural to the nutritional, highlight the remarkable diversity of the D block and its profound impact on our lives. Section 3. Magnetism and Color. Unveiling the secrets of electron configuration. One of the most intriguing aspects of transition metals is their ability to exhibit magnetism and produce vibrant colors. These properties arise from the arrangement of electrons in their d orbitals, those inner shells that hold the key to their unique behavior. Iron, cobalt and nickel, the classic ferromagnetic metals, owe their magnetic properties to the alignment of their electron spins. Imagine, if you will, tiny magnets within each atom, all pointing in the same direction, creating a powerful magnetic field. This alignment of spins is a consequence of the way electrons fill the d orbitals. In ferromagnetic materials, the d orbitals are partially filled, and the electrons prefer to have their spins aligned, creating a net magnetic moment. The vibrant colors of many transition metal compounds also stem from the behavior of d electrons. When light interacts with these compounds, the d electrons can absorb certain wavelengths of light and transition to higher energy levels. The absorbed wavelengths correspond to specific colors, while the remaining wavelengths are transmitted or reflected, giving the compound its characteristic hue. Think of the deep blue of copper sulfate, the emerald green of nickel chloride, or the vibrant purple of potassium permanganate. These colors, a testament to the quantum nature of light and the intricate dance of electrons within atoms, are not merely aesthetically pleasing, they provide valuable insights into the electronic structure of these compounds. And so, as we marvel at the magnetic properties of iron or the vibrant colors of transition metal compounds, let us remember that we are witnessing the elegant interplay of quantum mechanics and the periodic table, a testament to the beauty and order of the natural world. Stay tuned to Sperlin TV and don't forget to subscribe as we continue our exploration of the elements, unraveling their secrets and discovering their profound impact on our world. Section 1. Gallium to krypton, from semiconductors to noble gases. Welcome back, fellow explorers, to our grand tour of the periodic table right here on Sperlin TV. Today, we venture into the fourth period, where we encounter elements crucial for modern electronics, from the gallium in our smartphones to the krypton in our energy-efficient lighting. Gallium, a peculiar metal with a low melting point, literally melts in your hand. But don't be fooled by its softness. Gallium arsenide, a semiconductor compound, forms the backbone of high-speed transistors and lasers, enabling faster communication and data processing. Imagine the lightning-fast internet speeds we enjoy, thanks in part to the remarkable properties of gallium. Germanium, a metalloid with semiconducting properties, paved the way for the transistor revolution. Before silicon took center stage, germanium transistors amplified signals and enabled the miniaturization of electronics, laying the foundation for our digital world. Arsenic, often associated with toxicity, is also a crucial component of some semiconductors and plays a role in strengthening alloys. Selenium, an essential trace element, protects cells from damage and is used in solar cells and photographic toners. Think of gallium, a metal that melts in your hand, yet forms compounds that power our smartphones and illuminate our homes with energy-efficient LEDs. Germanium, the forgotten hero of the transistor revolution, paving the way for the silicon age and the digital wonders we rely on today. These elements, from the seemingly mundane to the technologically indispensable, highlight the remarkable diversity of the periodic table and its profound impact on our modern lives. Section 2. Germanium to bromine, transistors, catalysts and photography. Continuing our exploration of the fourth period, we encounter elements that have shaped our world in profound ways, from the bromine that captured memories to the transition metals that drive industrial processes. Bromine, a reddish-brown liquid at room temperature, played a crucial role in the history of photography. Silver bromide, a light-sensitive compound, was used in photographic film to capture images, preserving moments in time for generations to come. Krypton, a noble gas, finds its niche in energy-efficient lighting, emitting a bright white light when electrically charged. Imagine the energy savings and reduced greenhouse gas emissions, thanks in part to the use of krypton in fluorescent lamps and some LED bulbs. Meanwhile, the transition metals in this period, including iron, cobalt and nickel, continue to play vital roles in various industries. Iron, as we've seen, forms the backbone of steel, while cobalt is used in high-performance alloys and rechargeable batteries. Nickel, known for its corrosion resistance, is used in stainless steel, coins, and even electric guitar strings. Think of bromine, capturing fleeting moments on photographic film, preserving memories that would otherwise fade with time. Krypton, illuminating our world with its cool, efficient glow, contributing to a more sustainable future. These elements, from the nostalgic to the forward-looking, highlight the enduring legacy of the periodic table and its ongoing impact on our lives. Section 3. Unveiling the inner transition metals. A glimpse into the F block. As we delve deeper into the periodic table, we encounter a unique group of elements nestled at the bottom, the F block elements, also known as inner transition metals. These elements, often referred to as the lanthanides and actinides, possess a mystique all their own, characterized by their complex electron configurations and intriguing properties. The lanthanides, named after the element lanthanum, are a group of 15 metallic elements with atomic numbers ranging from 57, lanthanum, to 71, lutetium. They are often referred to as rare earth elements, although they are not particularly rare in Earth's crust. Lanthanides exhibit remarkable magnetic and optical properties, making them invaluable components in various technologies. For instance, neodymium is a key component in high-strength magnets used in hard drives, wind turbines and hybrid vehicles. Europium and terbium are used in phosphors, materials that emit light when excited by electrons, finding applications in fluorescent lamps, television screens and even euro banknotes. The actinides, named after actinium, are a group of 15 radioactive elements with atomic numbers ranging from 89, actinium, to 103, lawrencium. They're all radioactive, meaning their nuclei are unstable and decay over time, emitting particles and energy. Think of uranium, the heaviest naturally occurring element used as fuel in nuclear power plants and in the production of nuclear weapons. Plutonium, another actinide, is a byproduct of nuclear fission and a key component in some nuclear weapons. These elements, while less familiar than their main group and transition metal counterparts, play crucial roles in various fields, from energy production to medical imaging. Their unique properties, stemming from their complex electron configurations, continue to fascinate scientists and drive technological innovation. Join us next time on Sperlin TV as we venture further into the periodic table, exploring the heavier elements and unraveling the mysteries of their nuclear properties. Don't forget to subscribe and hit that notification bell so you won't miss a single episode of this illuminating journey. Section 1. Antimony to xenon, from ancient remedies to modern electronics. Welcome back, intrepid explorers, to our grand expedition through the periodic table right here on Sperlin TV. Today we delve into the fifth period, where we encounter elements with a rich history, from ancient remedies to cutting-edge technologies. Antimony, a metalloid with a long and storied past, was used by ancient civilizations for medicinal purposes and cosmetics. Think of the distinctive black eye makeup worn by ancient Egyptians, crafted from antimony sulfide, a testament to the enduring allure of this versatile element. Tellurium, a brittle silvery white metalloid, finds its niche in alloys, solar cells, and even rewritable DVDs. Imagine the vast amounts of data stored on DVDs, thanks in part to the unique optical properties of tellurium alloys. Iodine, an essential trace element, plays a crucial role in thyroid hormone production, regulating metabolism and growth. Think of the importance of iodized salt in preventing iodine deficiency, a reminder of the subtle yet profound influence of elements on our health. Think of antimony, once used as a medicine and a poison, now finding new life in flame retardants and high-speed electronics. Tellurium, a relatively obscure element yet playing a key role in the storage and retrieval of digital information. These elements, from the ancient to the modern, highlight the enduring relevance of the periodic table and its ability to connect seemingly disparate aspects of our world. Continuing our journey through the fifth period, we encounter elements at the forefront of timekeeping and those that pose significant health risks. Cesium, an alkali metal known for its extreme reactivity, forms the heart of atomic clocks, the most accurate timekeeping devices ever created. Imagine the precision of cesium atomic clocks, losing less than 1 second every million years, a testament to the remarkable consistency of atomic transitions. Barium, an alkaline earth metal, finds use in medical imaging, providing contrast in X-ray examinations of the digestive system. Think of the vital role of barium sulfate, an insoluble compound, in allowing doctors to visualize the gastrointestinal tract and diagnose medical conditions. Radon, a radioactive noble gas, is a naturally occurring hazard emanating from the radioactive decay of uranium in rocks and soil. Imagine the invisible threat of radon gas seeping into homes and posing a significant risk of lung cancer, a reminder of the importance of radon testing and mitigation. Think of cesium, so reactive it explodes on contact with water, yet providing the heartbeat of our most precise timekeeping devices. Barium, aiding in medical diagnosis, allowing us to peer inside the human body without invasive procedures. These elements, from the timekeepers to the silent hazards, highlight the diverse nature of the periodic table and the importance of understanding both the benefits and risks associated with these fundamental building blocks of matter. As we traverse the periodic table, we observe recurring patterns in the properties of elements, like recognizing the repeating motifs in a grand musical composition. These periodic trends, governed by the underlying principles of atomic structure, provide a powerful framework for understanding the behavior of elements and predicting their properties. Atomic radius, the size of an atom, generally decreases as we move across a period. This trend arises from the increasing nuclear charge, which pulls the electrons closer to the nucleus, resulting in a more compact atom. Conversely, atomic radius generally increases as we move down a group, as electrons occupy higher energy levels farther from the nucleus. Ionization energy, the energy required to remove an electron from an atom, generally increases across a period due to the increasing nuclear charge, which holds the electrons more tightly. Conversely, ionization energy generally decreases down a group, as the outermost electron is farther from the nucleus and thus easier to remove. Think of fluorine, the most electronegative element, with its insatiable appetite for electrons, readily forming bonds with other elements to satisfy its octet. Francium, at the opposite end of the spectrum, readily loses its valence electron, making it one of the most reactive metals. These periodic trends, like the recurring themes in a grand symphony, highlight the elegance and predictability of the periodic table, a testament to the underlying order and beauty of the natural world. Join us next time on Sperlin TV as we venture into the final stretch of our periodic table adventure, exploring the heavier elements and unraveling the mysteries of their nuclear properties. Don't forget to subscribe and hit that notification bell so you won't miss a single episode of this illuminating journey. And so, my friends, we've reached the end of our grand expedition through the periodic table, a journey that has taken us from the tiniest atom to the vast expanse of the cosmos. We've encountered elements both familiar and exotic, from the oxygen we breathe to the uranium that fuels our stars. But the periodic table is far more than just a chart of elements. It's a testament to human ingenuity, a symphony of science that harmonizes the fundamental building blocks of our universe. It's a roadmap for discovery, a predictive tool that has guided scientists in their quest to understand the nature of matter and the origins of our cosmos. From Dmitri Mendeleev's ingenious arrangement to the quantum mechanical principles that govern electron behavior, the periodic table embodies the elegance and order that underlie the seemingly chaotic world around us. It's a reminder that even in the most complex systems, there are underlying patterns and principles waiting to be uncovered. Think of the countless ways elements impact our lives, from the lithium that powers our smartphones to the platinum that cleans our car exhaust. The periodic table is not just an abstract concept confined to textbooks, it's woven into the very fabric of our existence. It's a testament to the interconnectedness of all things. A reminder that we are all made of star stuff, forged in the fiery hearts of stars billions of years ago. And as we continue to explore the vast unknown, the periodic table will undoubtedly serve as our guide, illuminating the path to new discoveries and a deeper understanding of our place in the cosmos. Our journey through the periodic table may be coming to a close, but the quest for knowledge is never ending. As scientists delve deeper into the mysteries of the atom, they continue to uncover new secrets hidden within the elements. From the creation of new elements in particle accelerators to the discovery of exotic states of matter, the frontiers of science are constantly expanding. And with each new discovery, our understanding of the periodic table and its profound implications deepens. So, dear viewers, I encourage you to embrace the spirit of scientific inquiry. Never stop questioning, never stop exploring, and never underestimate the power of the human mind to unlock the secrets of the universe one element at a time. And what better place to continue your exploration than right here on Sperlin TV? Subscribe now and join our community of knowledge seekers as we delve into the wonders of science, technology, and the natural world. Together, let's unlock the universe one element at a time.